Now we're going backwards a bit to chapter 10 in the book and talking about parametric equations for curves. You can talk about the parametric as the adjective, or you can also say parametrized. I might use that word sometimes. And you can talk about the parameter or parameters. We'll start with one parameter and we'll call it t. Well, oftentimes you can think of it as time. And there's a picture of a parametrized or a parametrized curve or parametric equations. That's usually how it gets said. It's that loop-de-loopy curve. I just made it up, and you should think of it as the path of perhaps a flying insect or a small plane or a spaceship, whatever you like, a little robot flying through the air, and t is the time, and it tells you where the picture shows where that location is at each time. Now you can have negative t values or positive t values, and this one I have t equals -5, and then I put t equals 0, and then 1, 3, and 10 just for some examples. But the arrows should always point in the direction of increasing parameter, increasing t, or increasing time if you want, so that you can see where it's heading next. And you can describe any curve by telling where x and y are for input t. So this is how you write the equations for such a curve like that. It's two equations. You can call the curve c for some, or something else if you want. C is pretty common for curve. And there's two functions, x equals f of t and y equals g of t. For t, an element of some range of real numbers, say from a to b. And you can call the position at t, given maybe a time t0, just for that's just a specific one, not necessarily equal 0, but just some specific one. It might be -5 in that above picture. And it's the point x comma y is equal to f of t0, g of t0 for that specific t value. So now you can see how it works. You can write down any that you want. We'll do an example very soon. We have seen these before. In 3.9, chapter 3.9, calc 1, related rates. There's often a pair of equations where x and y both depend on time. So there's a lot of examples in that chapter of real life situations. And there's also these kind of curves where they have x equals x of t and y equals y of t, the position of the spaceship or the ship or the insect, whatever you like. And there on the left I did mention that sometimes we skip that f and g and just call it x equals x of t and y equals y of t. That's faster and more efficient, and as long as it isn't confusing, we can go ahead and just call the function the same thing as the output. So here's an example of one. I have the picture started on the side there, but we'll work up to that. Here's the curve itself. X equals 2t and y equals 8t cubed plus 1 for t an element of -1 comma 2. Okay, so that means any t value between -1 and 2. And so first thing I did is just plot some points. To plot points for these, you need to pick t values and then find the x and the y, and then you actually plot the point x, y. So for t equals 0 and -1 and 1 and 2, and then I did some half points over there too. T equals 1/2 and -1/2. I picked a bunch of values in between -1 and 2, not necessarily in the right order. I just was thinking about which ones to pick, and so I put them all in the t column. And then I calculated the x and y values, which is pretty straightforward. X is 2 times t and y is 8t cubed plus 1. So like when t is -1, that's the very first one on the picture, you get -2 for x and -7 for y. And there's the point that I plotted, -2, -7 at the bottom of the picture. And then I plotted the other points, and I drew the arrows to show that that's the direction as t increases from -1 to +2 at the very end, where you get 465. Alright, so that's basically how you plot points. And next we'll look at the same example and try to see how we can relate the picture of the big picture to the individual equations, 2t and 8t cubed plus 1.